Imagine for a moment that it disappeared. In an instant, without warning, a fundamental force we take for granted simply ceased to exist. What would happen? The first thing you would notice wouldn't be falling upwards, but rather a loss of grip. You, your chair, a table, everything not bolted to the floor would gently drift into the air, continuing to move at the Earth's rotational speed. But Earth itself would no longer be a single entity. The immense pressure in its core, contained by gravity, would burst outwards with the force of an unimaginable explosion, tearing our planet apart. The atmosphere, no longer bound to the planet, would instantly dissipate into the cold vacuum of space. The oceans would boil and evaporate. The moon, breaking free from its orbit, would shoot off in a straight line into interplanetary space. The solar system would unravel. The sun, a giant ball of plasma held together by its own gravity from nuclear self-destruction, would explode as a supernova. The entire universe, from galaxies to clusters, would turn into a chaotic expanding soup of matter, devoid of structure and order. This thought experiment, however apocalyptic, vividly demonstrates one simple truth. The force of attraction, or gravity, is not just what makes apples fall to the ground. It is the silent architect of our reality, the invisible sculptor who shaped the universe and continues to form every aspect of our existence. The history of our understanding of gravity is the history of science itself. The ancient Greeks, Aristotle in particular, believed that objects fell to Earth because they sought their natural place, the center of the universe. He argued that heavier objects yearned for it more strongly and thus fell faster. This idea, based on intuition rather than experiment, dominated for nearly 2,000 years. It was only during the Renaissance that Galileo Galilei dared to challenge this authority. Legend has it that he dropped balls of different masses from the famous Leaning Tower of Pisa, demonstrating that they hit the ground at the same time provided air resistance is ignored. He showed that all objects accelerate towards Earth at the same rate. Galileo described how objects fall, but the question of why they do so remained unanswered. The answer came from a man who, according to another well-known legend, pondered this very question after seeing an apple fall in a garden. In 1687, Isaac Newton published his seminal work, Philosophia Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, in which he formulated the law of universal gravitation. His insight was brilliant in its simplicity and universality. The very same force that causes an apple to fall to the ground also keeps the moon in orbit around the Earth and the planets in orbit around the sun. Newton's law states that any two objects in the universe attract each other with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This means the more massive the objects, the stronger their gravitational attraction. And the farther apart they are, the weaker their attraction, with this force diminishing very rapidly as distance increases. This elegant formula revolutionized the world. It allowed for the prediction of planetary motion with incredible accuracy, the calculation of comet trajectories, and the explanation of tides. Suddenly, celestial mechanics was no longer a divine mystery, but a solvable mathematical problem. Gravity became a known, measurable, and predictable force, governing the cosmic dance. But its influence isn't limited to celestial bodies alone. Gravity is the universe's primary architect. Approximately 13.8 billion years ago, the Big Bang created space, time, and matter. Initially, the universe was an almost homogeneous, incredibly hot, and dense soup of particles. However, within it were tiny, random fluctuations in density. In places where there was slightly more matter, gravity was a tiny bit stronger. And this tiny difference proved crucial. For millions of years, gravity slowly but unwaveringly drew matter from less dense regions into denser ones. These denser regions grew, accreting more and more gas and dust. Thus, the first structures began to form, giant clouds of hydrogen and helium. Within these clouds, gravity continued its work. It compressed the gas, causing it to condense and heat up. When the pressure and temperature at the center of such a collapsing cloud reached a critical threshold of millions of degrees, a thermonuclear fusion reaction was ignited. Hydrogen began to convert into helium, releasing a colossal amount of energy. At this moment, a star ignited. Every star we see in the night sky is a triumph of gravity, a titanic nuclear reactor held back from exploding by its own colossal weight. Gravity compresses the star, while nuclear reactions in its core create pressure that strives to tear it apart. A star's entire life is a delicate balance between these two forces. When a massive star runs out of fuel, gravity claims its ultimate victory. It compresses the star's core with such force that it collapses, causing a cataclysmic explosion, a supernova. This explosion scatters heavy elements forged deep within the star: carbon, oxygen, iron, the very building blocks of ourselves and our planet, throughout the cosmos. And the remnants of the core can collapse into exotic objects where gravity reaches its extreme limits: neutron stars or black holes. But gravity doesn't only create stars. Around young stars, protoplanetary disks form from the remnants of the gas and dust cloud. Within these disks, tiny dust grains accrete, forming pebbles, which in turn collide and merge into asteroid-sized clumps called planetesimals. The gravity of these planetesimals continues to draw in matter and other smaller bodies. This process, known as accretion, continues for millions of years until fully formed planets, such as our Earth, are created. Gravity not only created our planet, but also gave it its shape. It was gravity that caused the molten material of the young Earth to coalesce into the most energetically favorable shape, a sphere. It also carried out gravitational differentiation. Heavy elements such as iron and nickel sank to the center, forming the core, while lighter silicate rocks remained on the surface, creating the mantle and crust. This process continues even today. Gravity is the driving force behind plate tectonics. It pulls dense oceanic plates down into the mantle at subduction zones, triggering earthquakes, forming volcanic arcs, and creating mountain ranges. Even mountains themselves are the result of a struggle between tectonic forces, which push them upwards, and gravity, which seeks to flatten them through erosion. Let's return to the surface of our planet. Gravity dictates the rules for everything that exists here. It holds our atmosphere, a protective ocean of gas that provides us with oxygen to breathe, shields us from harsh cosmic radiation, and burns up most meteors. Without gravity, the air would simply dissipate into space. It governs the water cycle. Evaporated water rises upwards, but gravity forces it to condense and fall back to Earth as rain and snow, feeding rivers that, driven by the same gravity, flow to the sea. The gravity of the moon and, to a lesser extent, the sun creates tides. This eternal rhythm of the ocean that influenced the evolution of life in coastal zones and is still utilized by humans today. But gravity's most profound influence has been on life itself. Every living creature on Earth is a product of evolution under constant gravitational pull. Our skeletons are astonishing engineering structures, designed to support our weight and counteract the force of gravity. Our muscles evolved to allow us to move in a gravitational field. Our cardiovascular system must work against gravity to pump blood to the brain. We even have a specialized organ for sensing it, the vestibular system in the inner ear, which, with the help of tiny crystals, otoliths, informs the brain where up is and where down is. Plants also wage a constant battle against gravity. They have evolved strong structures such as lignin in wood to grow upwards, towards sunlight, overcoming the constant pull. Roots, conversely, exhibit positive gravitropism, meaning they grow downwards in the direction of gravity to anchor themselves in the soil and find water. Even single-celled organisms are capable of sensing gravity and reacting to it. We can observe the effects of weightlessness in astronauts. In zero gravity, their bones begin to lose calcium, muscles atrophy, and the cardiovascular system weakens. The body, freed from the need to constantly fight against gravity's pull, begins to adapt to the new conditions, and these changes are detrimental upon returning to Earth. This once again demonstrates how deeply gravity is woven into the very fabric of our biology. For over 200 years, Newton's theory was an indisputable truth. It worked flawlessly. But in the early 20th century, small discrepancies began to emerge. The most famous was the anomaly in Mercury's orbit. The planet did not move exactly as Newton's equations predicted. The discrepancy was tiny, but it existed and it troubled scientists. Furthermore, Newton's theory implied that gravitational influence was transmitted instantaneously. If the sun were to suddenly disappear, Earth, according to Newton, would immediately fly off its orbit. This contradicted the special theory of relativity, then gaining momentum, by a young physicist named Albert Einstein, which asserted that nothing, not even information, could travel faster than the speed of light. Einstein spent 10 years developing a new theory of gravity, and what he proposed in 1915 was not merely a refinement of Newton's theory, but a complete paradigm shift. General relativity, GR, posits that gravity is not a force in the conventional sense. It is a manifestation of the curvature of space-time itself. Einstein suggested visualizing space-time as an elastic fabric, much like a stretched trampoline. Massive objects such as stars and planets depress this fabric, creating indentations or gravitational wells. Other less massive objects moving nearby, for example, a planet orbiting a star, are not actually pulled by a force. They simply follow a straight path through this curved space. An orbit is, in essence, a straight line in curved space-time. An apple falls to Earth not because the Earth pulls it, but because the Earth has curved the space-time around itself, and the apple simply rolls into this well. This revolutionary perspective not only perfectly explained Mercury's anomalous orbit, but also yielded several astonishing testable predictions. Firstly, GR predicted that gravity should bend not only the paths of material objects, but also the path of light itself. This was confirmed in 1919 during a solar eclipse, when astronomer Arthur Eddington observed that light from distant stars passing near the sun was indeed deflected by an angle precisely predicted by Einstein. This phenomenon, known as gravitational lensing, is today a powerful tool in astronomy, allowing us to see distorted images of distant galaxies whose light has been magnified and bent by the gravity of closer clusters. Secondly, the theory predicted that time in a strong gravitational field should pass more slowly. This effect, called gravitational time dilation, sounds like science fiction, but it is a real, measurable fact. Clocks aboard GPS satellites, located further from the Earth's center and in a weaker gravitational field, run slightly faster than clocks on the surface. If engineers didn't account for this relativistic effect, the GPS system would accumulate an error of several kilometers every day, rendering it useless. Every time you use your phone's navigation, you are practically proving Einstein right. Perhaps the boldest prediction was the existence of gravitational waves, ripples in the fabric of space-time itself, that should arise from the accelerated motion of massive objects, such as the merger of two black holes or neutron stars. Einstein himself doubted that these waves could ever be detected due to their incredible faintness. But a century later, in 2015, the LIGO Observatory made history by directly detecting gravitational waves from the merger of two black holes more than 1 billion light-years away from us. This signal, lasting mere fractions of a second, was the echo of one of the most powerful events in the universe, and its discovery opened a completely new era in astronomy, gravitational wave astronomy, allowing us to hear the cosmos rather than just see it. Einstein's theory provided us with a profound understanding of gravity, but the story doesn't end there. Modern physics stands on the threshold of new mysteries, and gravity is once again in the spotlight. The main problem is that general relativity, which describes the macroscopic world, is incompatible with quantum mechanics, which describes the world of atoms and subatomic particles with incredible precision. We don't know how gravity behaves in the microworld. Does the hypothetical force-carrying particle for gravity, the graviton, exist? What happens to spacetime at a black hole's singularity or at the moment of the Big Bang, where density and gravity reach infinite values? The answers to these questions are expected to come from a future theory of quantum gravity, a theory of everything that will unite the two pillars of modern physics. Furthermore, observations of galaxy movements and the universe's expansion rate indicate that the visible matter we can observe is catastrophically insufficient to account for all the gravity we detect. This has led to hypotheses about the existence of dark matter, a mysterious substance that neither emits nor absorbs light, yet possesses mass and, consequently, creates gravity. It is believed to account for approximately 27% of the universe's mass energy, whereas ordinary matter constitutes only 5%. Moreover, it has been discovered that the universe's expansion is not slowing down due to gravity, as one might expect, but is, on the contrary, accelerating. This phenomenon is attributed to the action of an even more mysterious dark energy, which acts as a kind of anti-gravity, pushing space apart. It accounts for approximately 68% of the universe. Thus, 95% of our universe is composed of something whose nature we have not the slightest idea about, and we know of them only through their gravitational effects. Indeed, from a falling apple to warped spacetime, from the formation of planets to the very structure of our biology, from the Earth's tides to the ripples from merging black holes, gravity permeates everything. It is the weakest of the four fundamental forces, yet it is the most long-range and dominant on cosmic scales. It is the force that forged order from primordial chaos. It is the conductor orchestrating the majestic celestial ballet. It is the anchor that holds us to the surface of our small world, hurtling through the vast cosmos. And while we have come a long way from ancient myths to Einstein's equations, gravity still guards its deepest secrets, beckoning us to peer beyond the horizon of knowledge and comprehend the fundamental laws that govern our universe.